you to this wonderful gathering. It is a beautiful September evening here where I am in Pune, and we have an exuberant audience from across the world. Before I begin, let us spare a moment to remember the contribution of every engineer on this planet. That professional, that ardent dreamer without whom we would not have these amazing creations dotting the planet. So, on the occasion of Engineers' Day, warm greetings to all the engineers, architects, construction and design professionals, and oh, yes, the many students who have logged in. We appreciate your presence here and thank you for attending. Friends, like music and lyrics, the partnership between architecture and engineering gives rise to symphonies that are heralded as masterpieces. As an art and a science both, it is the collaboration between architects and engineers that allows the human being to conceptualize, create, and enjoy some of the greatest structures in the world, coming from the trained hands of experts who are maestros and masters. Yes, it is truly, truly teamwork. From the client who says, I want a building that will be a showstopper and yet fulfill my expectations of economy and design and construction and beauty, to the architect and structural engineer who give wings to this dream, to the actual men who work long hours on site. I think today's program is a beautiful tribute and a salute to the spirit of being an engineer in heart and mind. Friends, we are happy to introduce this webinar titled Masters of Structure. Today, we shall be chatting with an individual, an institution really, who has not only helped many internationally acclaimed architects to realize their iconic design, but has also engaged with students and is a gentle guru to so many engineers. I'm honored, ladies and gentlemen, to welcome you to this gathering and to welcome to the gathering Dr. Joeseph Colaco, affectionately called Joe or Dr. Joe. And now, without further ado, I request Jain Kulkarni from Epicons Friends of Concrete to give the preamble and first to tell you a little about EFC, which is Epicons Friends of Concrete. Before I hand over to Jain sir, I request all the members of the audience, the panelists, and everybody to please keep their audio on off so that we can focus on the subject in hand. Over to you, Jain sir.
Good evening, everybody. I wish you a happy New Year's Day. The New Year's Day is celebrated in the name of Sir Mokshagundam Vishweshwaraya. He was an extraordinarily intelligent person and a very strong engineering sense, and he was awarded Bharat Ratna. Engineers are really a gift to humanity. They are responsible for development as well as creating safe and stable structure. On this occasion, we are glad to announce a series of conversation with masters of structure, an appropriate way to celebrate Engineers Day. This will enable us, all engineers, to understand many master engineers. This idea came from our senior friend and colleague, Abhay Ghate. He has very elaborate hands-on experience in structural design for more than 50 years. He has designed many complex structures and tall buildings in India and abroad. During this process, he met many versatile and intelligent engineers and architects. Abhay has worked with Joe Palazzo on few important interesting projects, and Joe Palazzo believes that best structural system comes out only when architecture and engineering integrate together. An excellent example of these things happening together is engineer Kamal Hadkar. He is an outstanding structural engineer who is called architect engineer. Mr. Kamal Hadkar did Herculean efforts while designing Stock Exchange building at Mumbai and Indraprastha Stadium at Delhi, demonstrating engineers' art. He is the ideal person to introduce us to the salient features of Zoopalace's contribution and art of engineering. This is beginning. We have many intelligent and great talented engineers around us, and now shortly we'll be conversing with them. Thank you. So this completes my preamble. Priya, now we can go to the
Can you
next
tell the
slide.
audience a little about EFC?
Yeah. So you can start the EFC slide, friends. Epicon Friends of Concrete is a knowledge sharing platform since 1999. It works under title Epicons Consultant Private Limited, ISO 9001 2015 certified company, and one of the well-defined objectives of Epicons is imparting technical knowledge to interested parties and society at large. Next. Epicons practices in the field of structural design, project management, architecture and engineering, assessment testing, and infra. Next. At the same time, I must mention that our principal inspiration comes from our friend, philosopher, and guru, late engineer A.K. Remedios. Next. EFC has conducted 81 workshops in last 23 years and 39 webinars in last 2 years. We started webinars since lockdown. Next. The topics which we normally cover are codal provision, complex structural analysis, advanced concrete technology, deep foundation, construction chemical, waterproofing problems and solution, earthquake engineering, seismocritical footing, and renewable energy. And one of our thought leaders, Professor Dr. Yogendra Singh, he will be addressing our next workshop. Next. And our team consists of, apart from myself, Anand Kulkarni, Ravindra Deshpande, Arvind Parolekar, Parashar Mogi, and P.P. Pandey. Thank you. With this, I complete my introduction.
Well, friends, we move on to the next point on our agenda. These are the structures that we shall be discussing today. And now I would like Engineer Kamal Hadkar, Chairman of Sterling Engineering Consultancy Services, to introduce our guest, Joeseph Colaco. Kamal sir, over to you.
Thank you very much for giving me this opportunity. And thank you, Jayant, for inviting me to introduce Dr. Joe Colaco today. I can say that I'm one of the fortunate engineers who got opportunity to work in collaboration with Dr. Joe Colaco very early in my life. Interesting story. One of our clients, a very wealthy developer in Mumbai, was keen on constructing a tall and slender tower at a prestigious location in Mumbai. Since stability against earthquake and wind forces was of prime consideration, I suggested the name of CBM, a Houston-based consulting engineering firm, as advisor. I had read about them in technical journals, and I was very impressed by what they had done and successfully designed that 80-story tall building, if I'm not mistaken, in Los Angeles, where people were very reluctant to build tall structures. And this tower was designed by using outriggers to control deflections. So I was attracted to this particular concept. So until I reached CBM's office in Houston, I had no idea that this name was coined by three brilliant structural engineers from India, namely Colaco, Banawalkar, and Mahindra. I was pleasantly surprised to find that they were very friendly and showed me their latest complex projects and answered all my queries. Very soon, we became great friends. Although Joe started his career in Chicago and rose to fame in Houston, USA, he has not forgotten his roots in India. I used to be very impressed by his enormous energy and innumerable journeys around the world to develop business connections in China, Middle East, and India. To the best, he was not fussy about formal contracts with the clients. He always trusted them even in their difficult times. His extraordinary quality was that he could think simultaneously like an architect, the owner, and like a contractor. Hence, his advice was always found to be the most appropriate. Joe and I bonded well while developing the ambitious Palais Royal project in Mumbai. I will not talk about other projects now because the list is very big. Before I close, I want to emphasize that simplicity and modesty are his remarkable virtues, which I must mention here because he himself will not talk about them. He did not ask his clients to book a room or a suite in a luxury hotel. Instead, he preferred to stay with his sister in Mumbai, eating home-cooked Goan food. Another amazing ritual religiously followed by him was his favorite game of tennis in the morning with his old friends. He did not bother about jet lag. I can keep talking on and on about this Superman, but I have promised Jan that I would not take more than 2 to 3 minutes because all of us are eagerly waiting to hear Dr. Joe Colaco. I thank you, Jayant, once again for giving me this opportunity and pass on the mic to you. Thank you.
Thank you, Kamal sir. Moving on now, we come to what we are here for. I hand over the mic now to Abhay Gate. Abhay, all yours.
Good evening, all of you. It's a pleasure and honor to know Dr. Joeseph Colaco, and we know him as Joe, and have a conversation with him. Joe and I have worked on working on an ongoing 5 million square feet development in Delhi NCR. Heinz engaged our services as structural consultant, and Joe was directly engaged by Heinz as advisor to the client. For the first time in Gurgaon, we are designing a 5-basement structure and 5 towers with high atrium. I attended several design development meetings in Cesar Pelli's office in New York and many online meetings with Joe. Joe had a razor sharp analytical mind and a remarkable quality of understanding the architectural intention and the concept of the architect. He listens to the architecture presentation with rapt attention, absorbing all the constraints. In the meetings, Joe is miles ahead of others. He waits for others to arrive, and when you finally catch up with him, you find that he has surveyed the whole area, explored all alternatives, and chosen and lit the best path. Joe has his views on choice of grids, floor-to-floor heights, to minimize the cost of the 5-basement structure, design of diaphragm wall, and the most appropriate structural system to resist lateral loads and gravity loads. It was a pleasure to get the required architecture tweaking done along with Joe. This informal conversation is aimed at getting the benefit of Joe's enormous experience in designing and detailing some of the most challenging and complex structures in the world, and his interaction with the architects, clients, and contractors. It is difficult to choose 4 projects out of more than 50 or 60 projects, tall buildings he has done. We have chosen only 4 projects to describe and touch upon his role in Burj Khalifa. So now I will request Joe to start. We have put the slides in a chronological order, and Priya will show the slide behind, and we can start with that. So first, Joe, I would request you to talk about tell something about yourself. How did you start about your life's journey?
Thank you, Abhay, and thank you, Kamal. It's very flattering, but a little bit exaggerated. Sort of by way of background, I was born and raised in Baikala, Mumbai, and went to school in Dobitalau at St. Xavier's High School, St. Xavier's College. And eventually, thanks to my father, I joined VJTI. He was the one who pushed me towards civil engineering. And I finished up at VJTI in 1960. That time, Professor Sen Gupta was the principal of VJTI. And then I went to work for 1 year with a company called Shalimar Tar Products, and they were building the first precast concrete factory in Bandung, which we did. I supervised the construction of that factory. And they did several projects in Mumbai using precast. It was kind of an interesting experience to get, and these were pre-stressed members, so the pre-stressing was involved. Then I decided to go to graduate school, and I applied to different places, and I got in at the University of Illinois, which is about 150 miles south of Chicago. And I completed my PhD there in 1965. And as I was sitting to complete my PhD dissertation, the phone rang in my advisor's office. And it was a gentleman named Dr. Fazlur Khan, who was a student at with the same advisor at Illinois 10 years earlier. And he was looking for an engineer to work on a 100-story tall building in Chicago. And for those young people today, I got to tell you, those days I was the computer nerd. I knew more about computers than anybody else. So I went up to Chicago and met Faz Khan, and he showed me the model of the building, which you see on the left-hand side of the screen. And my job then was to develop the structural analysis for that tower. Now, for those of you who are young people, I've got to tell you, in those days, the largest computer we had was an IBM 1620, which had 2 kilobytes of memory. And nowadays, you guys can do thousands of these in a second. But I spent many a night with punch cards in and punch cards out. And I had to do the complete analysis of the exterior frame of that building. Parenthetically, I want to tell you that this John Hancock Center in Chicago, I call it made in India because the boss man was Faz Khan from Bangladesh, from Dhaka. The senior project engineer was Srinivasa Iyengar from Mysore. The computer guy was me from Mumbai. And the project engineer was Mr. Shah from Gujarat. So all of us were working on this project, and that's how it got built. So I always told everybody it was built in India, or the brains of people who were educated in India. Anyway, it was a very, very exciting project. There are lots of things I can talk about if we had time. But I'll just mention 2 or 3 things. We broke a lot of ground on that project by putting diagonals on buildings. That was never done before on a major building like that. And that concept came strictly from the brain of Dr. Khan, who was a genius. And very, very hardworking. He worked harder than us young guys in the office. The second thing was, this is a multi-use building. It's got apartments on the top, office building below, and below that was parking, and below that was retail space. And then the original design was 2 50-story tall buildings, one for the office and one for the retail, for residential, side by side. And the architect, Bruce Graham, asked Faz, what would happen if we put one on top of the other? And for those of you who are starting engineering, we might just think about what would happen if you have a base, which is an office building, which has got a large footprint, and you put a 50-story residential tower on top. Obviously, you've got tremendous problems with transferring the vertical loads, forget the lateral loads, the vertical loads from the residential tower above to the office building below. And Faz told Bruce Graham, look, if you let me taper the building, I can make it a smooth thing without any transfer girders. And then if you let me put the diagonals on there, we can save a lot of money on it. Incidentally, they budgeted, in America, we budget everything to get the cost. And this was budgeted, a steel budget was 35 pounds per square foot. And we worked our head off, and we finally came in at 29.7 pounds a square foot. And I made the mistake one time in a meeting of telling somebody that we were close to 30 pounds a square foot. And Dr. Khan corrected me, said, no, Joe, it was 29.7. It was like selling shoes for $29.95. So I remember that. So I always say it's 29.7 pounds a square foot. But it was a very exciting project. We broke a lot of new ground on a lot of things like motion perception, floor vibration, temperature analysis, on and on and on. And the only thing I will, for the young people in the audience, I will tell you that this building is so designed with the spread of the gravity load that the wind did not, and I repeat, did not control the design. the wind stresses were so low in the building that all the members in the exterior frame are designed for gravity load. And that's one of the reasons why you could bolt all this entire structure together, and the connection details were very, very simple. I don't know how you want to do it, Abhay. Do you want them to ask questions now, or do you want to wait till later?
I think we could start with the questions of each project, because if you permit.
Yeah, that's fine with me. Whichever way you want to go.
I think the question on the John Hancock Center, my question would be, how did you handle the actual shortening of the edges, edge columns and other things?
The nice thing about a diagonally braced building is the axial shortening occurs obviously as you go up the building, but the diagonals distribute the load. And one of the things I found in the computer analysis was that no matter what we did, the stresses on all the exterior columns were the same. You can see from the vertical section through the building and the plan that the corner column theoretically has very little load on it. But when we ran the analysis, because of the diagonals, all the columns are the same stresses. So Dr. Khan said, okay, we're going to make, at any level, we're going to make all the columns the same size. And axial shortening, axial stress being the same, axial shortening was about the same. So that's how it works.
One small question about it. You mentioned that the idea of putting one tower on top of the other came up at the last minute. How much was the progress achieved before that? I mean, when this idea was introduced, where the foundations were already laid?
No, this was very, very early on. It was actually before I got there.
Okay, good.
Bruce Graham and Faz were just noodling one day, and they said, and Bruce just said, Faz, what would happen if we took one tower and put it on top of the other tower? And this is a tapered building, but just imagine two rectangles, one on top of the other. And the residential tower is small, got a small footprint, and the office tower got a big footprint. So all the gravity loads will come in at the transfer levels. And we had a 4-story truss system that was enormous in cost and weight, and the whole thing was a mess. So that's when Faz suggested, this was all before my time, suggested to Bruce that let's taper the building like this. And there are lots of problems with this. Obviously, every floor in the building got a different size, different layouts, and so on and so forth. But they went for it, and they convinced the client that being in a 100-story tall building, he could get more rent for the residential part, which is on top. And even being in a 100-story tall building, John Hancock would look down on their competition, which was Prudential, which was only in a 45-story building. Well, he got more money for all that stuff. So this diagram in the middle, by the way, is one of the things that's very interesting. This is what I found on my computer analysis. You can see that I took just two concentrated loads of 70,000 pounds on two columns right there at the top. And when you come down to the bottom, the load is so distributed that all the columns get the load, and each one's got 20,000 pounds. And so that shows you the distribution that the diagonals do as you go down the thing. Incidentally, Dr. Khan did not realize this. And when I showed him the numbers, he said, no, you're wrong. Go back and redo the analysis. And then talk to Mr. Iyengar about it. So I did it for days. I went on this thing. And then I showed it to Mr. Iyengar. And Mr. Iyengar said, no, you're correct. Go tell Faz that. I went in one Monday morning and told Dr. Khan, no, this is correct. This is what happened. And Faz looked at me and said, of course it happens like this. It has to distribute because the diagonals take the load and transfer them out. And I was a little butcha straight out of school. I was not going to contradict Dr. Khan. And I said, sure, Faz. So then he said, make all the columns at any level the same size. And that saved a lot of money. I mean, it was unbelievable. And the stress diagram on the right, you can't see it very well, but
one question, Joe, is was there no objection to putting diagonals? Normally, in the residential towers, clients, the architects do not allow any diagonals coming in the way.
Well, that used to be the way it was done, and they were very, very worried that those apartments which had diagonals in it would not be rented or have obstruction of the view and so on and so forth. Priya, can I make a sexist comment? Is it okay?
Yeah,
Well,
go ahead.
what they finally did was the advertising people took a very pretty lady, and they put her in the drape of the diagonal. There were two diagonals like this, and they put a pretty lady in there. And they took the pictures of that and put that in their leasing brochure. And every young man wanted that apartment with the diagonals because he had visions of getting a young lady in there. No, but to answer your question, that building has been 110% full from day one. And one other thing I'll just mention, you can go back to the previous slide. You can see the building right next to, see the building on the right? That's a 70-story apartment building. This building, the Hancock building, has got 90% glass. You can see out of the building through 90%. That other building to the right, which is very common apartment structure, has got only 50% glass. So the vision from the inside is much better in a diagonally braced building. But there are lots of people, lots of developers in the United States who say, no, I don't want to take that chance. So, but it's at the end, we had a very novice developer named Jerry Wallman. And he just said, if you can save me money and I can get more rent, that's fine with me. I don't care about all the other stuff. That's a win-win.
That's great.
We can go to the next one, One Shell Plaza.
Okay, One Shell Plaza was a defining moment for me. This one was the headquarters of the Shell Oil Company, and a young developer in those days named Gerald D. Hine from Houston came up to our office in Chicago, was working at Skidmore, Owings and Merrill, and was proposing to build this building for the Shell Oil Company. And the Skidmore, Owings and Merrill had done a 38-story building called the Brunswick Building in Chicago, which was a concrete building with columns based on 9-foot-4-inch spacing, because that was the module of the Brunswick Corporation. This one was a 6 feet, the Shell Oil Company worked with a 6-foot module. So all the columns in the building were 6 foot on center, like you see on the perimeter of this building. And the idea then was to do the concrete structure, and the concrete structure would be in itself a very efficient structure. But then we would just come in and put marble on the concrete elements, and that would be the finished product. So you can see on the left, all the concrete is right behind, and there's a piece of travertine that's 3 centimeters thick, applied directly like almost like a piece of paper or cardboard right on top of the concrete. So whatever size you got the columns and the perimeter beams, that's what the travertine was all about. And then this was one of the first what they call tube-in-tube building structurally. You can see the concrete shear walls in the core of the building. And then we had a perimeter tube with columns every 6 feet on center connected by a girder that runs all the way across. This is the fundamental structure that was used. Now, what we do there is then you got to do the floor framing. We have essentially a one-way, what we call a joist. It's like a concrete beam every 6 feet on center. So the column gets direct load from the floor. And the question became what to do with the corners. And Dr. Khan asked me to come up with every conceivable way to do the corners. And for those of you who are starting engineers, I might just quickly tell you there are 4 different ways to do the corner. The first is to continue the one-way beam structure vertically, and then put a girder horizontally where that red column is going to the outside. The other one is to reverse it and put the girder going vertically on the red column going down. The third one is to put a diagonal girder from the red column to the corner column. And the fourth is to build a corner waffle. And we examined all 4 of them. And the contractor finally decided the cheapest way to do is to go with the waffle. Then we did an enormous amount of calculations, because in a waffle system, you have what we call column strips and middle strips. So the strip right by the red column going horizontally and vertically have more load than the ones that are going in between. And so Dr. Khan told me, go ahead and figure out how the loads are distributed. And now this is where the interaction with the architects and engineers come in. In the old days, the architect would say, I don't give a damn what your structure is doing. I want all the columns uniform size. That creates axial shortening problems, which I can discuss if we have time. But FAS was very strong enough to convince the architect, no, we ought to build it naturally. So the load is higher, make the columns bigger. So if you look at the design of the columns, you have the blue columns coming right down with the red columns right below. Those columns are bigger. And as you get towards the corner, they become smaller, smaller, smaller. So that from an axial stress standpoint, all the columns on the outside have uniform stress. You don't have to fake it. You don't have to add reinforcement in some columns or the other. And so then you get the slightly wavy shape that you see on the perimeter of the building. But that's all natural to express the structure. The only one bad thing about this building, I still regret it. You see we have the core 4 shear walls, and just to the right and left of the core, 10 feet away, there are 3 columns. And there was tremendous axial shortening problems between the shear walls and that column. We ran, I don't know how many analyses I had to do with shrinkage creep analysis and so on. And I wish I could have taken those columns out. I still regret not taking them out, but anyway. But they were there because the 36-foot span is what the Shell Oil Company wanted. So we gave them 36-foot clear span all the way around the building. Now, I'll mention two more things on this building that are interesting. We have very bad soil in Houston. There's no rock, there's no hard foundation. So we have what we call clay. And so the only way we do these foundations for these buildings is to excavate soil of almost the same weight as the weight of the building. So you keep digging deeper and deeper. So that is what we call a floating foundation. So the heavier the building, the deeper you have to dig. So Dr. Khan said, why don't we do lightweight concrete? And so there were never building built with lightweight concrete this high. We spent 6 months with testing and all kinds of stuff to figure out lightweight concrete. And we ran temperature analysis on it, shrinkage creep analysis, all that sort of stuff. And then we ended up 6,000 PSI concrete, which is, I think, somebody will have to convert that to kilograms per centimeter square. Anyway, very high strength concrete. And this became the tallest concrete building in the world when it was finished. It was 714 feet tall and remained that way for a very long time till other tall buildings started coming up in Chicago and New York. And then eventually now, obviously, the Burj Khalifa is the tallest concrete building around. So it's got a lot of interesting features. We did a big temperature analysis. You cannot see this in the diagram, but the glass line is moved out as you can see a little better here. As the columns get bigger, you'll see a picture that says glass line. We moved the glass line out. So I ran a lot of temperature analyses on these columns to try to keep the temperature, average temperature on each column the same, so that under even temperature conditions, the building would shrink uniformly. So there was a lot of engineering went into this building.
So quite complex.
Yes.
What was the depth? The depth of the column strip was the same as the joist, or was it higher?
No, it was the same. We used 6 feet because that was a module that was set up by the Shell Oil Company. All their offices are on 6-foot grids.
I see. And the waffle, what you used, did you use the molds or did you have a specific?
They had square molds that were 6 foot square.
Yes.
And then they just dropped them and carried them up to the next level.
And the foundations you did on the raft foundations,
this was a very thick raft foundation. It was 8 foot 3 inches thick, and it went 20 feet beyond the profile of the floor plan, and it was also lightweight concrete. So even the foundation. So the building totally is lightweight concrete. The floors, the foundation, the columns, everything is lightweight.
Lightweight. The floors were in lightweight concrete. You mean?
Yes. Yes.
I see.
Everything.
Everything.
All concrete.
All concrete, columns, walls, floors, foundation.
Dr. Joe, what are the density of the concrete when you say lightweight?
Sorry?
Density
Lightweight?
of concrete.
The density is 115 pounds per cubic foot. Normal weight concrete is 150 pounds per cubic foot.
Okay.
So it saved a lot of weight, and therefore we made slightly shallower foundation. The foundation was still 18 meters deep, 660 feet below ground. So we had a huge excavation, retention system and all
How did you analyze the raft at the time? The Plaxis and the safe analysis were not possible. Actually, they were not there. Actually,
No. The soils engineer was a very, very bright guy. He and Dr. Khan and I sat down for hours. And he came out with a diagram showing like he had one pressure for the core, another pressure for the strips in the middle, and then in between he had a third pressure. And then we did a lot of strip analysis, as we called it, in different directions and all that. Essentially what we did was we take the analysis of flat slabs like we had in the old days, column strips, middle strips, applied it to the raft foundation.
So this must be one of the first buildings of tube in tube, isn't it?
I think it's one of the first, but I think the Brunswick building before this also had a tube and tube. I'm not sure it was done before my time, but Dr. Khan had proposed a tube and tube, I think in 1962 or 63. This one was 1968.
We have a sketch also of the axial distribution and other things also.
Yes, right. Yeah.
I
I spent quite a few hours on this one because I was a senior project engineer on it and also was working on the construction. So I used to fly to Houston every week to look at it.
Okay, we go ahead with the chase tower and then we come back if we got more questions.
All right. This is the JP Morgan Chase Tower, which is the tallest building in Houston. It's 300 meters high, 75 stories, 1,000 feet. And the reason it's stayed at 1,000 feet was the same problems you have in Mumbai, which is there's no height restriction in Houston, but there's restrictions for airplanes flying into the airports. The same thing happens in Mumbai. I remember we were doing in Worli 3 towers for DLF, and there were 97, 95, and 92 stories because of the air path to the Shivaji Airport. And this is the same thing. This was 1,000 feet. This was a very interesting project. For the first time in my life, I sat down on an architectural presentation. Mr. Hines and the banker, Mr. Love, conducted an interview of 7 architects, and they asked me to sit in on it. And so I sat in on it, and I began to see how important presentations were. Anyway, long story short, I.M. Pei was the second architect to be interviewed, and he was so impressive. Everybody just fell in love with him, and they let go with I.M. Pei. And so we started, I started working with Mr. Pei on this project. And do you have a plan of this? We can come back to this diagram.
Yes, we have a plan, yes.
If you have a plan, yeah, there you go.
Yes.
And what you can see is what they did was take a square, which is 160 foot on each side. That's about 52, 53 meters. And we have columns at 3 meters on center all the way around on 4 sides. But the 5th side, which is the bottom left, is open. There's no columns, anything at all. And that's a very long span. That's about 80 feet clear. So I.M. Pei himself came to me one day and he said, now, Joe, we got a ruptured tube. And we need to figure out how to heal the rupture, as he called it. So if we go back to the previous slide, I'll show you. Not this one, the other one. This one here. You can see the open side right there, which is 80 feet wide, with nothing. There's no frame, there's no nothing. So I went and we started working on this. I went and to the drawing boards and I said, okay, what would happen if I put diagonals across there? And just put like shoelaces. I call it shoelaces because we just put an X across there. And I showed it to Mr. Pei and he absolutely loved it. He thought that was the greatest way to solve this problem. And then he finally made a model showing the X's and all that. And the next time we had a presentation to Mr. Hines, Mr. Hines just came off the chair and said, no, no, no. He hated diagonals. He said, no, they're going to ruin my leasing. I don't want diagonals. All right, so I came back with another alternative, which is to put a stiff story. You can see those 2 horizontal beams. At every 10 stories, I was going to make it a truss. So there would be a truss, then 10 stories, and another truss and all that, just to put stiff story every 10 stories. And everybody that I knew liked it except Mr. Pei. Mr. Pei said, no, 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 I want this to be a uniform surface all the way across. So we played, and then Dr. Banavalkar and I sat down in the office. And go to the next slide. Can you go to the next one? Well, that's the floor plan. So we said, okay, we can't do anything on that surface at all. So what we did was we took the 4 sides of the building, which were a tube, and when we came to that big column in the left-hand corner, we went back into the core and put a very stiff beam to connect the shear wall in the core, and came back out another shear wall on this side, and then came back out again. So we connected internally to the core shear wall. Now, the thing about this building, which was interesting, was we were very worried about the weight of the building plus the construction time. So we got away from all concrete and did a composite building. So this is fundamentally a steel building with steel columns all on every one of these things. And we came back later on and poured concrete around all the columns to make them composite. And this thing went up extremely fast. They built the entire building in 28 months, all 75 stories of it. And these were the special problems we had to analyze: the foundation retention system, temperature analysis because the columns are half exposed, differential axial shortening, which we were talking about earlier, Abai, because we got some steel columns, we got composite columns, we have shear walls. Every one of them has got differential settlements. And then at the 60th floor, we dropped the shear walls off, so the top 15 floors were exposed. So we have a moment transfer problem for steel to concrete at that section, and that's the 60th floor. The ground floor is 65 feet tall, is about 20 meters. And so we have the problem of buckling of the shear walls. Now on the left, you can see the composite system going up. The steel columns go up first. And I suggested the contractor to take the rebar with him. And he thought it was a great idea. So as he built the steel column, he put the rebar cages right with the steel column. They went right on up. And in the bottom left, you can see the formwork system was very clever. They had took the gang 3 columns together with a form that could be moved like a sheet. And then there was a hinge, and you form the beam on one side and the column faces on the other side. And that thing was a godsend. It went so fast, it was unbelievable. They were building a floor every 3 days. And this is a very high strength concrete. In those days was 7,500 PSI, all normal weight concrete. And this for a long time was the tallest composite building in the world. It's been surpassed now. But you can see how logical the whole thing was. It just kept on going very, very quickly. In the middle, you can see in an intermediate place where the steel is up about 12 floors ahead of the concrete work. And then down below is the composite concrete that's wrapping all the steel columns, fireproofing them, and then wrapping the shear walls also were going on up. So the whole thing went up very, very fast. We have a raft underneath this one also. The raft is 9 foot 6 inches thick and is down 63 feet, which is about 20 meters from the surface. And these are all the different things that the guidelines that were put up by the Portland Cement Association, and talking about what different systems you can consider for different height structures and so on. Dr. Khan was instrumental in getting some of this stuff done. So we followed that very closely. At the 60th floor, you can see we got a transfer floor out there. So it's a very tall floor. But on the other side, you've got essentially a tube. You've got columns at 10 feet on center with a 4 foot 3 inch deep spandrel beam all the way around. The building is very rigid. It has the aspect ratio is good. For those of you who are engineers and want to know the deflection of the building under hurricane loads is height of a 700. It's a very rigid building.
Did you have the shear walls were also in composite construction, or shear walls were in concrete?
Yes, the interior shear walls were composite. So we left a piece of the floor slab out. They could slip form the shear wall, and they came back and filled the piece of the floor later.
And the connections were done, bolted connections, all the bolts.
Yeah, everything on the floor is bolted, yeah, except for that one girder that comes, is a steel girder that comes across from the major columns on the left and the right of the long face. Those are welded, but everything else is all bolted. Okay, now this is another building. This is a building, the architect on this building was Philip Johnson. And this is a building that's about, that's 5 miles away from downtown Houston. On the west side, it's called the Galleria area. And for many, many years was the tallest suburban building in the world. 64 stories tall, 936 feet high. And on the right-hand side, you can see some of the core plans. The core was pretty much defined by doing very fast construction. This building is all steel with metal deck, and the exterior columns here are 15 feet on center all the way around. It's a complete tube on the outside. There's no bracing in the core or anything of that kind. The entire wind load is taken by the perimeter tube. So the beams are 15 feet on center. So we have 3-inch metal deck, which is 75 millimeters deep. And the floor slabs are lightweight concrete. And what we did with this structure, so the column is 15 feet on center and the perimeter tube, we use the same erection technique that's been what we call tree columns. I don't know where this first came in. I think the original World Trade Center had tree columns. I know that for sure. But the erected the tree columns. And the thing that you engineers ought to know is that the one significant thing about this building, from the time we started construction to the time of first occupancy, was 14 months. This is the second fastest building ever built in the United States. The fastest was the Empire State Building during the Depression in the 1930s. But there they were working 2 shifts a day, and there's so much unemployment that they hired thousands of people to work on it. This was done under regular working conditions 5 days a week. But you can see on the outside, you can see those columns, the diagram right at the top. Those columns are 15 feet on center. So we had 3 columns that were built with a column 2 stories tall with arms sticking out. And they just kept on erecting that, and they bolted the intermediate connection. So there was going 2 floors a week, that fast. And then Mr. Hines decided to build a temporary roof for the 46th floor so that he could occupy the lower part of the building while the upper part was being built. And we put a temporary cooling tower, all the air conditioning and all that was done separately for that, to release the building fast. And then the finished building was done in 14 months. So from the start to finish, it was just an incredible, speedy construction. The diagrams on the top show you the stress levels in the columns, both on the flanges. You have a shear lag, as you can see on the flange columns. And then the web columns also have some shear lag, so that you don't have a perfect triangular distribution of stresses across the web. You get a little parabolic thing there. And so we looked at that very carefully, and then we began to call it like a channel system. So if you look at the diagram on the bottommost diagram, we have basically found very little stresses were going to the center part of the flanges. And so it was like 2 channels side by side being welded together. And the plan in the middle shows the core, and then the foundation was a big raft that went all the way across. And the raft was 7 foot 6 inches thick for this one.
And the
Very
floor
efficient.
system for the beam and deck system, deck slab system.
Right, just the beam. The beams are 21 inches deep, which is 55 centimeters. The slab was 3-inch metal deck with 3 1/4 inch lightweight concrete. So the entire slab is 160 millimeters thick.
And what was the approximate tonnage or something? Can you tell us something?
The total, I'll give it to you in, it's 24.5 pounds per square foot. If somebody could convert that to kilograms.
Yeah, 24.5.
24.5, yeah. And then they got a beacon on the top.
I wanted to know why bracings were not provided in this building.
Well, they were not required, because if you can develop, to me, if you can develop the perimeter of a structure as you go taller, it's much better than having a core. The cores have become more and more inefficient as you go taller, because obviously you want to get the largest lever arm on the wind resistant.
Yeah, okay.
Yeah, there's the beacon going off at night. That beacon rotates, by the way, 1 time every minute.
Wow.
Beautiful. Very nice.
Okay, this is the Burj Khalifa. On this one, basically, we were hired to do the peer review of the building. The building was totally designed by Skidmore, Owings and Merrill in Chicago. And EMAR, who was the developer of the building, asked us to do the peer review of the building, which we did. And the fundamental thing about this building is an all-concrete building. And going from the ground all the way to the tip of the spire is 2,800 feet, which is still the tallest in the world at the moment. And it's got a shear wall core, which is almost like a triangle. And then it's got columns on the perimeter at 30 feet on center, which is 9 meters on center. and a flat slab, all reinforced concrete flat slab, which is 9 inches thick. That's about 23 centimeters thick. And the construction was done by several companies joined together. The lead company was Samsung. And they built this building very, very fast. They were pumping the concrete all the way up. They pumped it almost 2,000 feet up. Now, there you go. Now you can see the core, which is like a triangular core. And then the perimeter columns are on the outside. There's nothing in between. And as the building goes down, you can see the petals going further and further apart. So the fundamental structure is a shear wall with flat plate as a frame. And the whole thing, as I said, 2,800 feet tall. Now, this is a pile foundation job. The piles are 60 meters deep. They go all the way down back into the limestone, which is very deep in Dubai. The shapes are all very, very good. And even the three-legged stool that's been done before. There's a building in Chicago called Lake Point Tower, 70 stories tall, which we did the peer review of that one a long time ago. And this is just a vertical extension of that concept. And there were 2 wind tunnel tests run at it, 2 foundations. Sheikh Mohammed of Dubai wanted this building to be absolutely fault-proof. And you can see on the right-hand side the pile foundation drawing for the building. And on top of that was a raft, which was almost 4 meters thick, raft on top of the piles. There's a big pile cap. I'm not allowed to talk about it, but the Sheikh Mohammed through Emar asked me to do a very private analysis on bomb blasts for this building. 9/11 had happened in New York to take the World Trade Center down. And so he wanted an assurance that there was no possibility of this building being brought down by a bomb. And so we did the analysis of progressive collapse on this building. And eventually I suggested some changes, which I cannot talk about. And then assured Sheikh Mohammed that there was no way any known terrorist could knock this thing off. Now, I'm not talking about unusual things like atomic bombs and stuff, but airplanes, suitcase bombs, none of that will bring this building down.
So we have some general
That-
questions on the whole thing. And we'll
Go ahead.
come back to technical questions. People are asking questions which will let you know on the whole thing. But one
Okay.
question which is uppermost in my mind is your interaction with the architect. Your work with legendary architects like Philip Johnson, IMP, Cesar Pelli, and some are good in geometric forms, some have postmodern architecture. But which architect stands out, in the whole thing of
Well, in my mind, the most brilliant architect of them all was IMP. He not only knew architecture, which he was very good at, but he also had a deep understanding of engineering, both structural and MEP engineering. And for example, when we did the JP Morgan Chase building, he's the one told me, I've got a ruptured tube. So Joe, what do I do about this? I didn't have to tell him that. He came up, he said, I know I've got a ruptured tube, but that's what I want. And that's why it's important to do this. So he understood that. When I talked to him about temperature analysis, he and his staff knew exactly what I was talking about. When I was talking about vibrations and all that, they understood all that stuff. So it was very, from a technical standpoint, it's a pleasure working with him in his office. On the curtain walls, for example, they had gone through the fiasco of the John Hancock building in Boston, where glass came flying out of the building. So they knew more about curtain walls than anybody else. And we spent hours and hours at the request of Mr. Hines supervising the technical design of the curtain wall, all the attachments, all the window wall testing. We were deeply involved in all that. And so from a technical standpoint, the total immersion in the project was very, very good. Other architects like Philip Johnson and Cesar Pelli, they did not understand the technical stuff. They were more the shapes and the forms and just the visual part. And if I told them that, like I worked with Philip Johnson in the Pennzoil building, and I told him there was some problem with the building being the trapezoidal building, and the shear wall core, which is the only resistance we had, was eccentric. So I wanted to move the core over a little bit to reduce the eccentricity. And he went through the roof. He said, no, I don't want this, and so on. We had to fight him because he didn't understand technical principles. He just wanted the view that he had of the building. IMPay was different. He understood. We explained it to him in 5 minutes. He got the solution. So there was kind of, I enjoyed working with Pei the best because he was more a team player. Some architects are like prima donnas. They want it their way. Priya, I'm sorry to say that, but you know what I'm talking about.
Yeah.
So it's all a question of, and there's a room for everybody, but I prefer just as a technical guy, I prefer we all understand one another. It makes it a lot more fun. And also the way Mr. Hines operated was make it a team. By like we worked on the HSIIDC project in Gurugram, the big for DLF and Hines, and you know how a team works. So there was a full team over there. You and I and the architect and all of us were together in job meetings and all Zoom meetings and all that. That makes it a lot more fun and much more. It really gives you a better result, I think.
And do you think the structural engineering profession gets its due recognition or something?
No, we don't. It's a lot of when you see the final recognition on projects, at most the owner will recognize the architect, and that's the end of it. And the reason being that in the marketplace, there is some advantage to owners if the architect's a name brand. Like this was designed by so and so, and he's got a name recognition in the profession. That's the sellable thing. And tenants will say, "Oh, I'm in an IMPay building, or I'm in a Philip Johnson building." But the engineer, if it's CBM or it's some other firm, that's got no market value to them. And then it gets very complicated. Obviously, you got to recognize so many people, there are 20, 30 consultants on every job. So we don't get the recognition, but the backhanded compliment we get is like from working with Mr. Hines for so long, is he would continuously use us for other projects. So it was a recognition of our ability to design a building well without any problem, design it economically and on time and so on. So that's the other recognition that you get, but you get it from the technical side, not from the marketing side.
But what do you do? Because, as big an architect like Norman Foster, didn't say a word when the Millennium Bridge was opened. And he remembered the engineer only when it started oscillating, So
exactly.
What do you do?
Yeah.
What do you do for getting this recognition? This is one thing.
Well, the only person I know that did this successfully is Dr. Khan. He would go out and start talking about it across the board. And I mean, everybody knew that the Hancock building was done by SOM with Fazlur Khan. So, and at the end of his life, they had named a street in Chicago for him, the Fazlur Khan
Yes, I saw it.
But he's the only one in our profession that managed that, and that he did with going public relations. And luckily for him, his peers like Bruce Graham and all that, they valued him so much. There were a lot of offers for him to leave SOM and join other firms. And he just stayed there, but they recognized his worth to the company. And so they gave him the recognition. But when you're an independent consultant, these architects don't have any hold on you. So they just don't want to recognize you. Luckily for us, there are certain owners, like Hines, like DLF and all that, who begin to understand the value that we bring to the party.
So my one question which is bothering me also, and I discussed this with Kamal also, that there's a lack of engineering judgment when people students, young engineers are using the computers, So there is over reliance on computers. So what is the advice you would give it to young professionals?
Well, they're going to get mad at me, but what I would advise them to do what Dr. Khan told me from day one. He said, before you go to the computer, do longhand calculations.
Exactly.
And so we would sit there and we try to figure out, how does this thing work? Like, you take a shear wall frame interaction. Where are the forces going? And I began to have a deep understanding of the distribution of lateral shear, how much goes in the shear wall, how much goes in the frame, and then you can start to play games with it. And by that, we also did some very preliminary sizing, which gave us then you didn't have to do so many iterations because you had some preliminary knowledge of the structure. And then when you got the computer output, you could make judgment. We have a saying in this country, garbage in, garbage out, GIGO. And I've seen so many ETABS runs in this peer review work that I do, that the guys have no idea whether the numbers coming out are right or wrong. And I sometimes tell them this cannot be done this way. The structures don't work this way. But they have no feel for that because they have never done longhand calculation. That's one problem with ETABS. Secondly, the ETABS that I've seen only put in the finished structure. They assume the structures are magically complete in one go, and you get these results. But during construction, there are a lot of things that happen in the intermediate. For example, if you got a transfer girder system, I've written 2 or 3 articles on transfer girders. And as you build a structure, the transfer is different because every time you build a structure, you got 2 floors, 3 floors, 4 floors, and the lateral load distribution, gravity load distribution is different. And so you have to take into account the enhanced values or loads that you get if you do a sequential analysis. Temperature analysis, the same thing. Axial shortening analysis, same thing. I can tell you some horror stories I've seen in peer review work I've done in Dubai and in India of people who don't understand how buildings work and they do things. And if Priya would not get mad at me, I'll give you some bad stories if you want.
I mean, have you noticed a significant difference between hand calculations and on the load pass and the work done on the computer machine?
Yes, I do. The one thing I found about these computer guys is they will, they go in and they make some assumptions, and then they'll. In India, when I was working in India, we used to call it gusau. They'll gusau these numbers in, and if the number come out okay, you got some certain benchmarks. You got lateral sway should not be more than such and such. If it comes out okay, go on. That's it. There is no optimization of the structure. There's no chance to massage the structure a little bit this way and that way to save cost. Cost is sort of not an important item to them because they just push it through the ETABs and out come the results. And sometimes there are fundamental things that are wrong with the structure or could be improved in the structure that they completely miss.
So what do you think of this new wave architecture defying form and defying gravity and odd shaped buildings coming up, especially in Dubai and Abu Dhabi? And so?
Well, that's what I call goofy architecture. Everybody's trying to be different. And there's some differences that you can do intelligently, and there's some are just goofy things that people come in and they build buildings that have got no shape, no size. It's all the stuff. They cut buildings this way. Sometimes they build buildings upside down, stuff like that. And I've seen so many buildings, especially in Dubai, that make no logical sense at all. I mean, I'm not talking about just keeping it, rectangular, square, but there's no logical shape for this other than it's a different building. And so they go and try to sell that project that way, and you go from there. It doesn't. I don't think that those buildings are going to last. They're one-offs. The cost levels of them are very, very high. I'll just mention one building in Dubai, which I did the peer review on. It used to be called the Infinity Tower. The building rotates as it goes up. It rotates 90 degrees. So the whole thing it turned 90 degrees. And I was talking to the owner's rep one day. We were having coffee. And he said, Dr. Colaco, would you buy an apartment in this building? I said, no. He said, why not? I said, because you're going to charge me more per square meter than a straight up and down building, right? Because it costs much more, 50, 60% higher. Oh, he said, yeah, but you're in a prestige building. I said, well, the prestige, you get the advantage because they'll say you develop the building. The architect will get the price for architecture, but I get to pay the price on the rent. And that building stayed unoccupied for quite a bit of time. And then eventually people began to go in the building. So these kind of things that are done for being different. And they don't make logical sense for engineers. All these engineers that work on these kind of projects are just trying to make the building stand up. There's no creativity and coming up with new ideas about it. Just don't let it fall down. So they end up being uh, monuments, but to themselves. They're not pushing the design forward. So I don't approve of that. But it's done a lot in the industry, as you know.
You have been
Sir,
you have been teaching in architecture school, isn't it? And what advice you would be giving to your students?
I basically tell them to understand structure just like they understand architecture. They need to know what gravity loads look like, how they work. They need to know how lateral loads are function, how you build the diaphragms to tie everything together. And then I teach a high-rise course. I start to get into axial shortening and these kind of issues that they have to worry. And they also, I take them to construction site and show them, if they do some goofy stuff, how difficult it is for the contractor to build these things, and how much time it adds to the project, how much cost it adds to the project. And so I'm just trying to make them aware that any design issues have consequences. I'm not telling them build the same building over and over again. No, there's a lot of creativity you can do without violating nature's laws. I mean, I'll just tell you, one student of mine wanted to build an upside down pyramid. So I asked him, why did you want to build an upside down pyramid? He said, well, sir, if I build a building like this, then when the sun comes, it'll shade the lower part of the building. So I said, okay, let's look at the sun angles. I said, in the morning, the sun is low, and the sun will come right into all the floors, right? It's only when the sun is up at the midday that you will get some shading. So 90% of the time, you're not getting the shading. So why are you doing this? And then I started to talk about problems. I said, on the second floor, you got no lease space. Third floor, you got 10-foot lease space. What are you going to do with all those floors? Oh, he said, I'll make it a big atrium. So you're just compounding one problem on the problem. I said, how do you wash the windows on this building? How do you hang the drapes? And he couldn't answer any of these questions because it was just a form that was different, and he wanted to do this. And so I gently told him that, you got to think about all these issues. And that shows you what can happen if people don't know what they're doing. They're just trying to be different for the sake of different.
That is correct.
You have been coming to Mumbai, I mean, quite often. What change you notice now?
Obviously, the buildings are getting taller, and you notice that immediately. The thing that Kamal Hatkar mentioned, that Palais Royal project, and his office and I spent quite a bit of time on that project. And it's essentially like an octagonal shape, which is very good from a wind load standpoint. But what we find is that if you can sit there and talk to an owner, for example, if you have a circular building, a round building, not used a lot, you will find that the amount of skin, perimeter skin on a round building is less, about 20% less for the same floor area than a rectangular building. So I tell the architect, my students, I said, look, that's 20% in your pocket, right? Then you've got less mechanical loads, heat loads, and all that. So why won't you do a round building? Give me the reasons why not. And they go through some reasons. Some of them get good reasons. And you get layouts are difficult, which I understand. But I said, you have to go through that thought process before you can say, I want to do this, I want to do that. I like this, I like that. You need to be aware of everything that you're doing, the impact it has on the owner, on the construction cost, construction time, and so on. So I think it's important to do the deep analysis of and understanding of these things.
Sir,
Yeah,
we'll
go ahead.
We'll take these questions put up by the attendees. Before that, I just wanted to ask, what is your opinion about the codal regulations? I mean, if are there any conflicts between your thought of your structural understanding and some codal regulation given by the codes or something like that? Any such experiences?
The Indian codes are by far the most prescriptive. They tell you you can do this, you can do that, and they go very deeply into deep things like the sway of the building and all that kind of stuff. Yeah. American codes and other codes basically tell you just the important things. The lateral load should be according to this wind code. Seismic is according to that code. But the Indian codes are much more prescriptive. They tell you this and that, and you have all that things done. But fundamentally, I like the idea of codes where they take the important issues and handle them. The one thing that eventually they're going to do is to get more and more involved in this progressive collapse thing. And thank God, so far there's not been any bombings in India, but with the World Trade Center bombing in the United States, these ideas of progressive collapse are coming back in the forefront now. They're not yet in the codes, but they're coming. And I think that's a good thing because it teaches engineers to think about things that could happen, eventualities as we call them.
One question, I forgot to ask is, we discussed 4 projects, but we did not discuss the project which in high seismic zones like Los Angeles, where CBM has done good work. Can you tell us something about it?
Yeah, that project in Los Angeles was done basically by my partner, Dr. Manavalkar, who's very, very good at seismic knowledge and so on. I'll just tell you 2 things. The first thing that he did on that project is there are some code prescriptions, but he did not believe that they went far enough for a building that was 1,000 feet tall. So we contacted a professor at Caltech and we hired him to come up with earthquakes that could hit that building because we thought that building being so prominent, we may have to go higher than code to get to design that building. So we came up with 2 what we call synthetic earthquakes, earthquake A and earthquake B. And we actually designed for those synthetic earthquakes that were higher than the normally prescribed earthquakes. So that was step 1. Step 2 was, IMP was the architect on that project. It was called Library Square when it was built, 73 stories tall. And we developed a perimeter tube on that building and we had to design it for all the ductility requirements on that you have in seismic design. At the same time, we had to control the drift of the building, both for seismic and wind, in order to be able to be sure that the facades wouldn't collapse and all that kind of stuff. So there was a very deep study of that project. We looked at so many alternatives on the structural systems, on different ways to consider that building. So it was quite an innovative way of building a tall building.
Okay, we can take questions of the audience.
We'll take questions from the participants. The first one is related to John Hancock building. Dear sir, what is the behavior of diagonal bracing under the seismic load? Diagonal seems to be multi-tiered. How does ductility was achieved?
Okay, first of all, in the days when we built the Hancock building, there was no seismic code in Chicago. Let's start there. Second day, you see, so there's no seismic code. We basically the wind design of the controlling element. Okay, there has been a big debate in seismic conditions where in California they came up with a so-called eccentric bracing methodology, so that you had the diagonals were not perfect like you see on this building, but they would stop short, not come to the nodal points. And that was so that the girder could develop ductility to get the thing done. I have a different thought on it. I still think that this concentric bracing has got good possibilities. And they finally built a building in San Francisco that's about 50 stories tall that uses perfect diagonal bracing, coming with nodal geometry. The thing about this is that those diagonals have very, very low stresses on them. The entire system has got everything is elastic. So even on seismic conditions, you could possibly, I'm not sure, we never did run a seismic analysis, that the seismic forces would not even put the steel into yield. The whole concept of seismic design is yielding of the steel elements provides the energy dissipation that you require in seismic design, so that you have damage to the structure in order to relieve the seismic forces. I'm also the opinion that we should try to keep the structures elastic, right close to the yield point, but don't exceed it, so that there's no major damage to the structure afterwards. So that debate is still going on, but I can tell you that concentric bracing is coming back on seismic design.
Yeah. So next question, I'll skip some questions, but I'll take important questions. How differential settlement was controlled in that foundation? In your
On the Hancock building?
Yeah, Hancock building.
We did not have any differential settlement to think about because as I mentioned to you, every column in this building, the exterior column, all had the same load and they all had the same foundation. And then they were all drilled piers, like the cast in place piles that went down 140 feet of rock. So the differential shortening of the piers was very insignificant.
Yeah.
And anyway, these construction of these diagonals will, if there is any differential shortening, they will equilibrate the structure so that they'll distribute anything very, very easily.
Thank you, sir. Next question is, does low density concrete not offer lesser strength and end up in higher sizes, thus ending up with same weight? Is it
The low density concrete, is that
having lesser strength or same strength?
No, we designed for the strength. What we did on the One Shell Plaza building, for example, even though we have low density concrete, we made the mixed design have 6,000 PSI, which is the highest concrete strength in Houston at the time. So there was no question between the density and the strength. Now, if you go to the modern concrete strengths where you're going very high, like 10,000, 12,000 PSI, that'll make a difference here.
Thank you.
Joe, Burj Khalifa, you use outrigger, but you generally prefer more peripheral frames. What is your preference between outrigger and peripheral frames?
I do not like outriggers. They're sort of a band-aid, as we call them. You try to make things work. To me, as you go taller and taller, you should totally develop perimeter systems and not even have a core. There's no reason to have a double system like this because the perimeter frames give you the most resistance of anything you can think of. So to that extent, the Burj Khalifa is not a very good structure because it relies on a core. And the core, as you can see, is so small, even though it's got the wings going off, you can see the wings that go up and down, but you don't generate the resistance from the entire perimeter of the building. So as you get taller, you should be going to a totally perimeter system, a complete perimeter tube. That's what you really need. Having a dual system with a core and another frame, that's not the ideal system to use. The other one thing I'll mention, Abhay, because we have some students over here, the one thing that disturbs me in the way buildings are built is I will hear from time to time, oh, here's the wind frame and these are gravity columns. These are only carrying gravity loads. So what it means to me is that some of the load in the building is not used to resist gravity. On the Hancock building, for example, when you've got gravity and wind being in one system, all the gravity load is resisting the wind load. Therefore, you got very little stresses on the columns from wind. Just to give you the stress levels on the columns of the Hancock building were less than 1/3 the gravity stress. And so there was not even an increase of size of the column because of that. And so you got a very, very efficient system. The whole building works essentially like a gravity system. And for the wind load, we only have these diagonals. That's why it's so economical to build it. So in my practice, I try very hard not to have this dual concept. Here's a wind system, here's gravity columns. I try to have it just one. It doesn't work all the time, I'll tell you honestly, but you should try to do that.
So the problem actually in Indian courts, in zone 5, particularly say in the highest zones like in Nepal or this thing, then perimeter frames, if you are to design for 25% of the seismic load, seismic shear, it becomes very onerous, you know.
Right, yeah, no.
Next question.
May I just add one thing here? Joe, this question is for you. We all agree with the perimeter, the strength and efficiency of the peripheral columns and the perimeter tube. Unfortunately, what happens is in India and especially in Mumbai, we talk to the clients about such systems and they say, no, we want to have maximum view. We want large windows. We don't want any column in between. So, we are forced to forget about structural economy. And even if we show them that this structure can save you so much money, they say the difference in the sale price is so high that we don't mind spending money on an uneconomical structure. So reluctantly, the structural engineer is forced to accept an inefficient or something that he doesn't like, that kind of structure. It's very sad.
It is sad, but we had the same on Hancock, as I mentioned to you, when we compared the Hancock building to a frame tube. But this is a diagonally braced tube compared to a frame tube. The Hancock building is 90% glass. Granted, it's got diagonal. Okay. A frame tube will have about 40% glass. So I can make the argument to an owner that you can get more vision in a diagonally braced building. But what they'll come back with is say, but where the diagonals meet, in that location, it's a bad place for me. So you sit down and you have to sit down with them and look at where the crosses are and say, okay, that occurs 5 times in the building. You look at this one, right in the middle where the crosses come together. That's the bad spot. I agree with that. And then the corner joint is also another bad spot. But they are very few and far between. The rest of the people have much more glass than anybody else. But I've not been able to sell that argument, Kamal, I'll tell you.
Yes, Joe, you remember we did one building successfully in Mumbai, Dadar, where you were doing the peer review for us. And we used diagonal bracings, and
I remember that one.
Perimeter columns were only 500 by 500 millimeter square columns, 5 of them. And that gave people plenty of glass on all sides. But in spite of the structural success, I don't see other people buying that idea.
Right. No. It is frustrating, you're right. But if somebody were to analyze it clinically, what you're saying is what I'm saying is the exact truth. You get more glass in a diagonally braced building than you do in any other. Dr. Khan, one of the last buildings he did was called on Terry Place in Chicago. It's an apartment building, and he built pseudo diagonals on the outside. It was very cleverly done. And it's what we call a partial tube concept. And I've used partial tubes in a lot of buildings, and people like them, but there are some people who say, hell no, I'm not going to use diagonals. So there's nothing you can do about it.
Yes. Can I just, as an extension to this question, I would like to know whether you have done any diagonals within the building, what in plane trusses, and leaving the perimeter columns free of diagonals. Is it possible?
Yes, we've done 2 buildings like that. One is in Minnesota called the Norwest Tower. The problem with that is it then begins to interrupt the interior planning of the building.
Correct.
You get these diagonals going through the floors.
Correct.
And then the question becomes, which is worse? And generally in American practice, they think diagonal inside the floors is worse. So, it's a matter of looking out or looking in, whichever way the client thinks is the best way to go. I prefer the perimeter diagonal like the Hancock building or like the Dadar building because it is clean, it's structurally efficient, and if you can convince the owner that you can actually get more glass than anything else, I think it'll sell. But there are some people who are absolutely opposed to diagonals. So,
yes, allergic. They're allergic to it.
Yeah, I know. And actually, the problem, Kamal, is in Delhi, although in Zone 4, some developers ask us to design for Zone 5. Which for Zone 5, dual system is a must. For having a dual system, we need columns. And when the columns become large, you lose. There's a conflict with the views, So we have
I know which one you're talking about, Abhay.
Yeah. Very interesting, Joe. It was very enlightening. I'm very happy.
Absolutely brilliant, So
I hope.
Some more questions you got?
Very few questions. We'll take 1 or 2 only.
Take 2 questions.
Yeah. How did you handle warping of core walls in JP Morgan?
The warping?
Yeah.
Again, you just have to design for it. We have a certain amount of warping, and Dr. Banawalkar is very good at that. He uses a so-called Vlasov concept to figure out how much the warping was and then design for it.
Okay.
That's all. And the last questions is I'll ask is have you worked any time on TMD, tune mass damper installation, and what is your experience on that?
We have zero real world experience on it. Luckily for us, none of the buildings we did required a damper. They were all designed without dampers. I've always felt that the damper is sort of a solution of last resort. If you can't make the damn building work, you got to do something.
Yes.
But we tried very hard to make the building work and not to use these artificial things like dampers and all that. Dampers are a mixed blessing. You know, they solve a technical problem, but they have tremendous cost impacts. Typically the tune mass dampers on the top floor of the building, the owner doesn't get to rent the top floor of the building. They have lots of maintenance problems. There are sometimes some of these dampers have a lifespan, sometimes 25 years, sometimes 50 years. And there are so a lot of issues with that. And so we have tried very hard to do buildings that do not require dampers. And so far, touch wood, we've succeeded.
That's great.
Joe,
Actually,
you are working, Joe, I believe you are working on a 1 mile high building. Can you tell me?
What happened was we had a recession here in the United States in the 1980s, and nobody had any work to do. And I was thinking about this, designing a mile-high building. I was asked to give a talk in Chicago to the ACI on how tall can you build a concrete building. So I just picked a number because engineers want numbers. So I took a mile-high building. And what I took was a Sears tower, which is a bundled tube, as it's called. And I extended it up to 1 mile high. And I brought together architects, other engineers, mechanical engineers, elevator consultants, and curtain wall consultants. And we spent every week, I used to take them all out to lunch, and we discussed the building and all that. At the end of it, for 6 months, I kept on working. And we did a very detailed analysis of the building, including wind analysis and all that. And then I presented the whole thing to the conference in Chicago. And because there was no work in the country, all the newspapers wanted to talk to me about my mile-high building. And then it was finally published in the Council of Tall Buildings and so on and so forth. I'm currently working on a different version of the mile-high building. That was done in concrete because concrete was the talk of American Concrete Institute. But now I'm coming up with a mixed use, like a composite building for a mile-high building. I'm working on that right now, just to keep my brain occupied. So.
Excellent. Joe, just one last question. What do you think of these two buildings which have come up in New York, which are extremely tall with extremely high slenderness ratios of, 25 and 30 and 40? I mean, they don't make any sense at all. They're just lacking.
No, they do make sense if you've got about $100 million for a penthouse apartment. That's for ego people. For example, the Steinway Tower, which is the one I've been looking at recently, is the tallest one now in New York. The aspect ratio is 1 to 24, just so in case you're looking at aspect ratio.
Yes.
They have a gigantic tune sloshing damper on the top of that building.
Correct.
It is incredible. And you talk about views, there's so much structure, even some of the perimeter walls are solid concrete. So the views are totally distorted. But it's an ego thing. Does it make sense? No. If you're going to do a mile-high building, the building's got to be tapered in some fashion. You can do a building like Hancock. That's one. The Burj Khalifa, which is gradually tapered as you go up. But a needle building going straight up is like a man sitting on a pole. I mean, it's just, it's got so many issues. The previous buildings done, they've got issues with partitions that are cracking, mechanical systems, and on and on and on. Well, these people, they have the ego problems. They don't have the deep understanding of what can happen in a tall building, and you got to worry about it. But I think it sends the wrong message that you can build these buildings like a needle and you pay a fortune for them. And then they charge these tax evaders enormous sums to buy the building. Incidentally, most of these buildings are unoccupied. They're money laundering schemes. So anyway.
I guess so. I guess so.
See, Kamal, Dr. Khan once said, any good engineer can solve a problem. Great engineers eliminate the problem.
That is
Yes,
correct.
correct.
I've never forgotten. I've never forgotten that.
We have to thank you for Joe for a very enlightening
Well, thank you for inviting me. It's always nice to come back home and
Can I
let
just
me
say
take
something?
it to Jan to. Yeah, we'll
In fact, I don't have any different words to thanks Joe. Only thing is, we should have at least one complete session for one project that can really explain various engineering aspect to the engineers who intend to learn. So first of all, Joe, thank you so much. Then I must thank Kamal, who is also, and I wanted some assurance from him that next time he will come for interview. And lastly, I must thank.
Jayant, you like grilled stuff or what? You want to? You're going to have a grilling session.
Well, I'll tell you, Jayant, you offer me a masala dosa and I'll come.
Because what tempted me about Joe was on one side he was designing complex and high-rise building, on second side he was teaching constantly. So everything what he has done, he probably can teach all the upcoming engineers. So we must have one session from him. And last but not least, Abhay Ghati, because this entire idea came out of his mind. So I thank him for giving such a brilliant idea of having conversation. And all the dear audience or participant, thank you. With this, we end our session. Thank you.
Thank you very much, Jan. Bye-bye. Thank you.
Thank you very much. Have a lovely Sunday.
Okay, thank
Thank
you.
you. Thank you.
Jen, sir, would you like to say something before we close?
You're asking me?
Yeah.
No, he has already thanked.
Okay.
No, I always say thank you.
So thank you very much. I'll just say one last thing. I'm an architect, and whatever I heard just now, I have always been excited about structures and buildings and all that. But it's just a thought that if every architect, we do have great teachers who teach us engineering, but somehow, it's a fact that the students of architecture somehow don't think that engineering is as exciting as architecture. And I'm 100% sure that after this session, every single student who returns to his architecture school on Monday is going to think of civil engineering in a very different way.
Well, let us hope so. Yes, very, very good thought.
On this note,
they have Priya. They have their own reasons why they find engineering not so attractive. But that we will discuss on another session session.
So, ladies and gentlemen, we are announcing that this program is over. Thank you very much once again for every single person who was here. Thank you very much and have a lovely Sunday tomorrow. Thank you.
Thank you. Bye-bye.
Bye. Bye.
Bye. Bye, Abhay.
Bye. Bye. Bye.